Okay, so in the previous recording lecture, we looked at functions of multivariables, like multivariable functions, so functions of n variables. So these functions take as input vectors and they spit out a scalar. We also learned about partial derivatives and the gradients. Now we're going to focus on specific types of multivariable functions, linear and affine functions. The most simple types of multivariable functions, but one of the most useful types of multivariable functions. Okay, so I think it's best to maybe start with an example of how what we know about vectors can now be applied to create functions. So maybe suppose A is some n vector, so it's a vector with n elements. Okay. Okay. Then f of x equals to A inner product x is the inner product function. Now, by definition of the inner product, f, the input vector x needs to have the same size as A, 10 dimension. So that means that f is a function that takes as input an n-dimensional vector. And we know that the inner product of two vectors is a scalar, so it just spits out some real number. So for example, if A is equal to 3, 4, and 7, then f of x equals to 3, 4, 7 inner product x. X has to be three-dimensional vectors to match up. So the x1, x2, x3. So then the inner product of two vectors is just the multiplication of the corresponding elements and adding them, right? So this is just going to be 3 times x1 plus 4 times x2 plus 7 times x3. Does everyone see how that works out? So just maybe I should probably just say recall A transpose A inner product x, so A times x is equal to the sum I equals 1 to n of AI times xi. We covered that in a previous lecture, so this is the inner product. If you forgot that, I know you haven't seen it in too many lectures thus far. Okay, so I think that yeah, I'll just illustrate it. I'll illustrate the next property with this example, this inner product function. So I'm going to let alpha and beta, these are just going to be scalars. They're just real numbers, okay? and x and y be in vectors. Okay, so now notice if we're looking at the inner product function, so now notice the inner product function satisfies so f of alpha times x plus beta times y. Well, what is this by definition? It's A transpose, I mean, it's A times X, right? So A inner product, whatever's inside here. So this would be okay, that's just some vector and we're multiplying it by A. Okay. But then we know by the one of my previous lectures that the inner product is distributive. So I know that this is going to be A times alpha x plus A times beta y. But I know that multiplication of scalars is cumulative. Sorry. So now I can write this as alpha times A times x plus beta times A times y. Oh, but now this is f of x, right? If that's the inner product, this is f of x and this is f of y. This is alpha times f of x plus beta times f of y. This right here is we've just shown that that is equal to that. Okay. So I'll call that equation there, this form of any equation that looks like this with a function. So this has a name. So functions satisfying, I'll call it equation double star. Are called linear. Now, I know in the back of your mind, possibly, you think back to like scale, like functions of one variable, and you think of linear functions as lines, but formally, a function is only linear only when it satisfies this. If you have a scalar times input plus scalar times input, f evaluated at that, if that's equal to the first scalar times the function at the first input plus the second scalar times the function at the second input, if this holds, then it's called linear, and only when this holds. That's the formal definition of being linear. So this might not look like much, but this really does say a lot here. So what this is saying is that if you input a sum of vectors and you can scale those vectors by whatever scalar you want, this combination evaluates to scalar times function plus scalar times function. It says more than you think, and we'll like we'll understand why as we deal with more linear functions, or as we are exposed to linear functions. In general, so in general, I should probably note this. So in general, a function is linear. That says linear when f of alpha 1 times x1 plus dot 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 plus alpha n, or what did they use? K. Alpha k times xk is equal to alpha 1 times f of x1 plus dot 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 plus alpha k times f of xk. Now, this is where notation is messy because these are vectors, they're not components. Please, please, please don't get that confused. Those are vectors and not the components of a vector. So if you have a collection of k vectors, a function is linear if this happens for any scalars, alpha 1, alpha 2, dot, 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 alpha k. Okay. Okay. So, what's an example, like a concrete example of a linear function? Well, this inner product function is linear because it satisfies that. But what's another one maybe? Maybe the average function. The average function should be linear. What is the average function? It's equal to 1 over n times x times x. Now, if that, so this is the average of the entries in the vector x. If that is not clear to you, you should go and make sure that you're staying on top of reading chapter 1, right? Because this is just the inner product of a vector with itself, which is the sum of, oh, wait a minute. One of you should have said something. There. The one vector times x. So this is just the vector of all ones. So it's 1 times x1 plus 1 times x2 plus 1 times x3, dot, 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 all the way through. So this is just summing all the entries in x, and this is dividing that sum by n, which is the number of entries. Okay. So is that function linear? Does it satisfy that? We can try and see what happens. I haven't done this, so hopefully it goes well. So let's just see if it is linear. So is the average function linear? Does this hold? So, okay. I sort of want to leave this as a homework problem, but maybe I'll get it started here. So alpha times x plus beta times y. So x and y are just n-dimensional vectors, alpha and beta are scalars. So this is going to be 1 over n times the one vector times x. Maybe I should write it like there. So the one vector times the input, whatever the input is, this. So, okay, and we know that this is distributive, so this is going to be 1 over n, 1 vector times alpha x. So I'm just going to move the alpha right here because I'm running out of room. Plus beta over n, 1 vector. Oh yeah, it's definitely here, right? Because now this is like alpha times 1 over n times 1 vector times x. So I'll just write it out. Alpha times 1 over n times 1 vector times x plus beta times 1 over n times the 1 vector times y. Well, that's right here. This piece, that's the average of x. In this piece, that's the average of y. So altogether, this becomes alpha times average of x plus beta times average of y. So average of this is equal to this sum. So it satisfies that equation, which means that yes, the average function is linear. Okay. What is next? Oh, our definition. So a linear function plus a constant is called affine. And affine functions appear everywhere in machine learning and in statistics, regression analysis. So they look like this. A times x, these are vectors. This is going to be a scalar, and then we add a scalar to it. That thing right there. Very important. For data scientists. This thing occurs all over the place. And you can think of it as, so in terms of linear functions and affine functions, why is it important for data scientists? Affine functions let's see the best way to describe this to you. Can take as inputs feature vectors representing data and output a weighted sum of those features. A weighted sum So imagine, for example, your input vectors were like housing data. So for example, in my house, there would be 3 bedrooms would be like the 1 entry, 2.5 baths would be the second entry, like 13 years would be the 4th entry for how old the house is, so forth and so on. And you could feed that housing vector into an affine function, and the entries in A can weight how important each of those features are in that sum plus some number, and you'll see why that exists later, can somehow give you like an expected value for your house, right? If you know the correct coefficients of those variables to stick into the A vector, you can predict housing prices. If you give a bunch of features in as a like number of bedrooms, number of bathrooms, how old, blah, 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 feed that in, then an affine function can spit out an approximate of how much the house should sell for. Okay. Now, are affine functions linear functions? Right? Because they look linear. Okay? Because this by itself is a linear function, but do affine functions satisfy that property? So just remember that, I'll just write it out again. Linear means that f of alpha times x plus beta times y is equal to alpha times f of x plus beta times f of y. Right, that's what it means to be linear. Okay. So, are affine functions linear? Not all the time. Not all the time. But if alpha plus beta is equal to 1, then this function behaves like a linear function. Oh, I almost forgot. Terminology about affine functions, before I forget. So A can have several names. The first name I would give it are weights. And the second name I would give it would be coefficients. So those are coefficients or weights. And then B has 2 names. It's either the bias or the intercept. Why would it be called the intercept? Well, when x is the 0 vector, B is on the origin. It's not the origin, it's on the output axis, right? Things like this lines in R2. If x is 0, then B is just how far up or down you are on that vertical axis. So, all right, so now if alpha and beta equal to 1, then affine functions satisfy equation double star, the one that, so this is double star. So they behave nice like linear functions. Now, a word of caution, some textbooks, some things you might read will refer to affine functions as linear, but this is not true. Not all affine functions are linear, and it's actually a homework problem that might assign to show that there are affine functions that are linear. Basically, finding values for B and A where no matter how hard you try, you can't make it satisfy that. It doesn't take long. Okay, so that will conclude my lecture on linear affine functions.